Okay, yes, thanks. Okay, so that work was mainly done by Nicola Lang, and also some proofs were done by Simon Stasny. Now, happily, now I don't switch. Okay, I don't have to introduce about Rydberg atoms. So the setting is this beautiful platform where we trap individual atoms by optical tweezer and excite them into a Rydberg state. And I've already seen there are two types of typical experiments which we can perform. One is that we use the ground state and the Rydberg state as a two-level system. And then the typical Hamiltonian is that we have the tuning, we have the strong van der Waals interactions, and we can control excitations by the Rabi frequency. And there are very many beautiful results, experimental results, like and especially also like the proposal to realize that two-spin liquids and first signature in an experiment by Mr. Looking. There are also alternative approach, which we just heard in the last talk, that if both atoms are if all atoms are excited into a Rydberg state, and we make an additional excitations into a p state, then we have the strong dipolar interactions, which means that these excitations can hop through the lattice. And here is an illustration which we done in the collaboration with Anton Brouwer for the experimental realization of a symmetry-protected topological phase. And if I have time, I would like to make two examples which are interesting in both settings. And I would like to start with the functional completeness of planar Rydberg structures. And I probably have to tell you exactly what I mean with that. So the goal is we want to implement a certain target Hilbert space. So think that you have at each, where you have an atom, you have a two-level system. And this gives rise to a large base Hilbert space, which is 2 in power of n. Now you want to select out of these states a certain target Hilbert space, which is separated from the rest of the states by a large energy gap, and all the states should be the generating space. And we want to achieve that with our Rydberg Hamiltonian, where we have turned on the Rabi frequency. So we just have a van der Waals interactions and a detuning. And for simplicity, let me focus on the PXP model, where we have a blockade radius where the interactions is infinity within the blockade radius and 0 outside. Then we can achieve really at the complete degeneracy. If you add van der Waals potentials, then we will end up with a slight splitting of this ground state structure. And so what we mean with a Rydberg complex, it's a set of placement of my atoms with local detunings for my Rydberg atoms for a given blockade radius. Let me example why this could be interesting. And we have heard already this morning by the talk from Mr. Looking. So the goal is therefore that we decide that our low energy space is a certain target Hilbert space. It can, for example, be the ground state of a NP-hard problem, so that you implement your atoms and your detuning in such a way that the unique ground state which is defined is the solution of an NP-hard problem. That we heard by Michel Luckingstall and is pioneered by my chair here, Johannes Büchler. In my talk, I will focus on a little bit a different task. Let's construct pre-Hilbert spaces that we still have the degenerate ground state manifold, but it defines us that we don't have a product Hilbert space anymore, but a Hilbert space which has a certain gauge degree of freedom. For example, the ground state or the pre-Hilbert space of the toric code. Or, for example, the pre-Hilbert space of the Fibonacci ions. That means that we have a large configurations, which, for example, can be characterized by strings in our setup. There is a very natural approach to achieve this, and this was pioneered by the Harvard group and then experimental probe by Mr. Looking. So if you place Rydberg atoms on a link of a cargo mail like this, then the Rydberg blockade automatically gives you these very nice dimer constraints. That means that you can only excite the Rydberg state if there is no other atom occupied in the Rydberg state touching this site. And this is an example where we have such an interesting target Hilbert space automatically implemented without having to do a lot. But the question is, what other interesting examples are there out there? Can we actually construct any target Hilbert space which we want? And this is what I would like to present you, and especially that it is complete, that with Rydberg structures, you can engineer whatever you want. So let me therefore formally tell you a little bit what is the language, how we would like to present it. So I formally define what is a language. So it's a set of classical binary variables with a Boolean expression f of x equal 1. And these are all the binary strings which satisfy this condition. And this is just a certain string set. Let me make an example. Oh, no, let me first continue. And then I define the target space which I want. I take these classical bits, and now I define out of it a quantum state. And my target Hilbert space is the span of this allowed target of my allowed state, which satisfy the constraint that fx satisfy s of x is equal to 1. Let me make a very simple example. And this is the copy language, which we'll see later. So if you have a bit, you want to copy it. So the A side is my bit, which I want to copy. And then I have two outputs Q and R, which just copy the bit. And therefore, if A is 0, my two outputs should also be 0. If A is 1, the two outputs should also be 1. And this is a very simple example of a language in the following form. And you can immediately see that with Rydberg blockade, one can very easily implement this language. Because if you arrange them, if you take 4 atoms, arranged in this way, the circles are the blockade radius, and the red means that we have 3 times the detuning from the blue sides. So then we can either place a Rydberg atom here, and it blocks the blue qubits. So it means that the blue sides actually realize the state 0, 0. The other possibility is that the center side is empty, and therefore it's preferred to excite all the blue atoms into Rydberg state. And that is the state 1, 1, 1. So we can immediately see, and therefore the ground state is completely degenerate in this picture and implements this copy language. An important message is that in general, we need additional ancillas to implement any arbitrary language. And for this simple example, we needed 1 ancilla to add to the system. Now, as said, I'm interested in pre-Hilbert space, so let's extend this to local constraints. So we have a lattice side, we have some physical states which we're interested. There can be a single qubit on each link. And then we have a local Boolean expression, which tells me which configurations are allowed in this configuration. And these are like stringlets, so it tells me that a loop entering a site is not allowed to end. So there must be a loop going out, or there must be, we can, like Torah code, we can require that the number of loops entering a site is an even number. And in that way, I can extend this formalism to languages which are translational invariant and extend for the full lattice. And I would like to prove you or demonstrate you in a sketch of a proof that Rydberg atoms are functional complete. So whatever language you want to implement, you can achieve that with Rydberg structures. And the proof is constructive. So I have to tell you in 4 steps how to achieve it. So first, and we have to go back a little bit in classical quantum, not quantum information science, namely that every Boolean expression can be decomposed into the NOR gate. So the NOR gate is functional complete, and every Boolean expression can be expressed as a product of NOR gates. We might have to copy the information input, and therefore one can draw this Boolean expression as a graph. So here are the input bits. Then you see we just copy it at some point. So we have the copy language, which is the solid point. So if I have to use this input twice, we just copy 2 places. Then we have the NOR gate at some point, and we link as arrows this information flow into our system. And then there is the output bit, which is my Boolean functions, which we're interested in. The first thing which has been noticed in the 70s is that this abstract graph can be implemented in a planar structure. So that means that we can deform our strings which are plotted here into loops which have space. By dots, I can vary link on the graph. But in general, you will see that there are crossings. So for example, if we implement here, you will see that we have crossings in our graph. And it was shown already in the 70s that actually crossings can also be implemented as Boolean expression. So this is the structure which you have to add at each crossing of the setup, such that you can implement it actually embedded in a planar structure. So that we know from all times that we can embed such a Boolean expression into a planar structure. Now we just have to implement every logical operation with our Rydberg atoms. And it's clear that the simplest one is just a link. So we have, if you want have here an information flow. We just want to move it through the system. And this we can always achieve by adding an ancilla in between. So we can link with arbitrary distances information flow to one to the next side. Then the copy language I've already presented you. And for functional completeness, there's also the NOR language, which has exactly the Boolean table of the NOR language. And for Rydberg atoms, the minimal setup, how to achieve it, is actually 5 atoms, which means there are 2 ancillas required. The important thing is that it's always a trivalent graph. So we can attach another incoming line to all of these input and output ports. And so what means actually combining languages or building now our graph structure out of these elementary building blocks, that's what is called amalgamation. And in Hamiltonian language, it just corresponds to adding up the Hamiltonians. So you just place your Rydberg atoms in the right geometry, and the total Hamiltonian is the sum of all local Hamiltonians which you had for your local Boolean expressions. And if you now want to make it on a lattice, now we have our local check functions, Boolean expression. Here you see that that's my result from Boolean expressions. If I just want to allow all states where the Boolean expressions is 1, then I add a large detuning to this value, and this selects me these expressions out of the ground state. So I can drop this out, add a detuning, and the combination is again just achieved by amalgamation of the different circuits. Now the proof which I presented you goes a little very rigorously through. Keep in mind that it's a constructive proof, so the setups which achieve in this way is not optimal. So for example, naively, if one follows the rules, this is the expression which one would obtain for a crossing. So a crossing means I have 4 inputs, and it will need a lot of atoms actually in this setup. If one optimizes it, there is a very simple structure which is shown here. And I have to mention this crossings was actually pioneered, was another 2 months before we noticed it, already appeared in an archive by our chairman, HansPeter Büchler, in a different paper, where they actually noticed that this expression represents actually a crossing of our setup. Now, what can we do? So let's go to the task and implement the Torre code, the pre-Hilbert space of the Torre code. So the Torre code was already introduced this morning. The pre-Hilbert space is that we drop the A term, which makes, and just focus on the B term. So the B term is the constraint that the spins surrounding a lattice site, there must be an even number, must be up, spin up surrounding. So there can either be 0 spins pointing out surrounding a lattice site, 2 or 4. In other words, we can characterize it by a loop. So a spin up is a piece, and therefore at every lattice site, there are 2 loops allowed to come in, there are 4 loops allowed to come in, or 0 loops. Now we can express that as a Boolean expression, and this is my language, and I will define my pre-Hilbert space as all allowed configurations which can be represented as such a loop. The true Torre code is afterwards constructed by this loop condensation proposed by Venn. That means that you make the equal weight or a certain weight superposition of all this allowed configuration. That step is still missing. We don't do the equal weight superposition yet. We really just construct the pre-Hilbert spaces, and then the hope would be that adding a Rabi frequency drives the system into the true ground state, which would be the Torre code. But this is now the setup which ends up with a minimal setup for the Torre code. So it requires per lattice site 7 ancillas in addition to the 2 qubits. Now I have to apologize. So the color always is the detuning which you have to add to the system. Ancillas are blue circles, and the physical qubits are square circles. I know it's a little bit hard, especially in my eyesight, but I know that in the original paper, it's much easier to see. And the color is the detuning. It's blue at the edge because it's on a finite size sample. So if you extend it to the full lattice sites, the Torre code can be achieved with a homogeneous detuning for the system site. And it's easy to check that, yes, these configurations has all allowed loop configurations of the Torre code. Or if you're interested in more fancy expressions, there are the Fibonacci anyons. So they have essentially at each link the fusion rules. So two Fibonacci anyons combining gives an Fibonacci anyon or the vacuum. One Fibonacci anyon coming in must be another Fibonacci anyon. That means it's a trivalent loop. There can be a loop is never allowed to end. It can be empty, but you can have three branches coming in. And again, this is the minimal configurations, how you realize it with Rydberg complexes. And so let's finish essentially my part about functional completeness. How much time do you see? Huh?
-2 minutes.
-2 minutes. Okay, then I should stop. Really? Don't I have half an hour?
5 minutes.
5 minutes. Okay, but that is a little bit. Okay, just let me.
We started a bit later. No, HansPeter. Oh, I see.
So I apologize, you have to listen for another 15 minutes. No, let me.
You have more.
Okay, so let me therefore switch my topic and tell you a little bit how actually we can also, so we have seen that there is this topological phase which one can realize on the Ruby lattice with just ground state and Rydberg state. I prefer a little bit of work in a picture where we have the dipole exchange interactions, and let me make an example where we can implement a topological phase with such Rydberg states. What we have to do is actually we place our atoms on a honeycomb lattice, and we choose 3 states in a Rydberg level. So we choose our ground state is that we excite all atoms into the Rydberg S level, and then we select the energetically 2 p states close by. Now you see, because we have an electron, we have spin orbit coupling, so the S state is twofold degenerate, and we focus on the p3 half manifold, which has 4 states inside. How can we select actually that these 2 states are energetically close by, apply a magnetic field that makes the 4 states tilted, apply an electric field that makes you either a smiley or an anti-smiley, combine electric field and magnetic field, and you can achieve whatever structure you prefer. And therefore, it's very easy possible by combining electric and magnetic fields to select that these 2, the minus state and the plus state, are close by. And I'm interested now that I have that 0 is the ground state, and I call, if I have a Rydberg excitation in the minus state, I call it the minus excitation, or a particle, a minus particle, or if I make a Rydberg excitations in a p state with a plus, I call it a plus particle. And these particles are naturally hardcore bosons. Now, if you look at the dynamics under dipolar exchange interactions, we have seen previously that under the xy, the particles can hop, but now we have 2 types of excitations. So therefore, this term here tells me that the plus excitations can hop through the lattice. That's like the S plus, S minus interactions we have just seen in the previous talk. But in addition, we can also exchange the internal angular momentum, because dipolar interactions has also the term here, where we have 2T plus, because it's an anisotropic interaction. And that tells us that if you have a minus excitations, you can de-excite it and excite a neighboring atom into a plus excitation. That changes the internal angular momentum by 2, and therefore we see here the phase 2 phi, the angle between the axis, which is the orbital angular momentum where it is transferred to. So because dipolar interactions conserves total angular momentum, but they can change internal angular momentum of the spin into orbital angular momentum. You can also just think what happens here is one atom emits a circular polarized photon, which is absorbed by the neighboring atom immediately, and therefore it picks up the phase of the circular polarized photon virtually emitted in a setup. Now, does it really work, or is this pure fancy in our system that we now have this double hopping? And we did with Antoine Brouwer a proof of principle experiment where we can actually see these phases, which allows us to engineer effective magnetic fields. And the setup is just 3 atoms in the Rydberg state. We choose them exactly in a setup as shown before. In addition, one can very easily understand what happens if one adiabatically eliminates the plus excitation. So that means an atom can hop, become a plus excitation, so a minus excitation can hop to the neighboring, become a plus, which is energetically forbidden, and then it hops further and becomes a minus excitation again. And during this hopping, it picks up the phase, which is exactly the angle enclosed by this hopping process. And what this tells us is that we have a hopping with a phase in our system. We have the direct hopping by minus can to minus hop, and we have the second order by the excitation of a plus excitation, which engineers an effective magnetic field in our setup. And by the strength of the two, we can tune arbitrary fluxes for our Dremel. So therefore, let's take the simplest flux which is present, which is a total flux of pi over 2. Then we know if we make excitations in the blue side, it will just hop around because we have a magnetic field, we have broken time reversal symmetry. So the excitation in blue will hop to the red side, to the yellow side, back to the blue, to the red, the yellow, and it doesn't disperse because we have chosen our flux at pi over 2. And this is the experiment. So we have a lot of spam error because we have to excite everything into Rydberg state. So we don't start at 1, but one nicely sees the oscillations. The blue atoms hops to side red, to yellow, to the blue, and runs around in a perfect circle. Now we can make a little bit a test and ask what happens if I make 2 excitation, because then I can distinguish whether these are bosons or fermions. So if I make 2 particles, and they are bosonic particles with a hardcore constraint, then I would expect the whole to hop in the opposite direction. If this would be fermionic particles, then the whole would hop in the same directions as previously. But now keep in mind, our gauge field is generated by a virtual process. So if I have 2 atoms, I cannot hop to my side for my virtual excitations because there's already an excitation there. So that means that the gauge field is turned off. And as a consequence, the dynamics is completely symmetric, as if you don't have a magnetic flux for the system. You are allowed to interpret it that the same dynamics you would see if you would place 2 anionic particles on this 3-level system, which have the exchange statistics of semionic particles. Because one particle has exactly the same flux as the external magnetic field, and therefore a hopping of the other particle is also an exchange, and it cancels you by the statistical phase, cancels the external magnetic field. Now, can we, with this setup that we know which works, can we produce topological states of matter? And let's combine it. So we choose our honeycomb lattice. Now we have our hopping, we have the diagonal hopping, we have the exchange hopping, which gives us our phases, and we have the hopping for the second type of excitations. In addition, we add a detuning, which fixes the total number of excitations in our system. Now I have to admit that we have to make a huge search in parameter space based on this beautiful software by Sebastian Weber for the pair interactions. So analyze really the microscopic parameters in our Hamiltonian, including van der Waals interactions, what lattice spacing we achieve. And the message is there's a very interesting point for these parameters here. There's one remaining parameter, which is the electric field. The gray area is where everything breaks down. And the green line is the point where I show you the numerical simulations where something interesting happens. Because what I will demonstrate you that if you choose the parameter at this point, the ground state is actually a fractional bosonic Chern insulator in a system. Now, maybe just shortly, how can we understand it? The goal is we have a honeycomb lattice. If you have a single excitations, it gives us a Chern band. So it gives rise to a band structure, which is characterized by a Chern number. One can make these bands relatively flat, even choose the parameter properly, like done here. And then one has a flat band with a Chern number. And then the hope is if one fractionally fills this flat band, one gets a fractional Chern insulator. And this is the idea how we search for it. But in the end, we had to do an extremely long search to find the parameters. But we found a very nice point where it's extremely robust. So the numerical tools to demonstrate that there is a fractal Chern insulator is exact realizations. We need to keep all 3 excitations on the lattice side. So we can only go up to 28 lattice sites for exact diagonalization. And we performed infinite DMRG on a torus. So the first signature is that there is at 1/4 filling an incompressible mod plateau done by DMRG, which tells us that there is a gapped state at the fractional filling appearing. Then, if you do exact diagonalizations, one sees a robust twofold ground degeneracy. So we choose different tessellations of the lattice to ensure that it is just not an artifact how we choose the boundary conditions to demonstrate that actually the excitation gap is robust and the near degeneracy of our system. We don't see any correlation functions. And if we add twisted boundary conditions, then the gap remains large. And in addition, we get a finite many-body curvature. And therefore, the ground state, the many-body ground state has a very curvature of C = 1. And the last tool is we can, in DMRG, extract the topological entanglement entropy. So put it on a cylinder, scale the size of the cylinder to larger values, and extract, in that sense, the entanglement of the half cylinder and make an extrapolation to a very large system size. And then one finds a very nice topological subleading entanglement entropy contribution, which is 0.5, which is completely consistent. So all its properties are consistent with the characteristic property of a μ1/2 bosonic Lovelock state. And then the hard task is how to experimentally prepare it, because we know if you want to adiabatically prepare the state by starting everything in the ground state, drive a microfield with a finite ramping detuning to generate excitations, we know that we must close the gap in our system because we are a true topological state. We cannot adiabatically connect the two states without a gap closing. And that happens if one very naively applies a global pulse sequence. One nicely sees that, yes, there's a point where the gap, so what is shown here is the excitation gap during the adiabatic ramping procedure. And one nicely sees there's indeed, unfortunately, extremely small excitation gap. But the answer is one can circumvent it by smarter ramping procedures. So don't do the ramping homogeneously, but actually do it inhomogeneously, such that in a center, the topological phase appears first, and then to push all the excitations to the boundary. And this is demonstrated here. So if in a center we first enter the topological state, and only later at boundary, you see that the previously finite size gap has completely disappeared, and we can do it, the ramping speed, with the final gap of our system, which is in the end just an edge states around our cylinder. And with that, I thank for your attention, and I'm open for questions. Oh, maybe, yes, if I have 1 minute for advertising a little bit. So I didn't speak about the Rydberg quantum computer platform we are building here. You probably will hear about it by Florian Meiner also a little bit, but just we don't have the beautiful setup like the Americans and already collaborating with Google, but we still have access to our online emulator. So if you're interested how we are supposed that our quantum computer will work in Stuttgart, you can already use our online emulator with up to 30 qubits. And there is also a drag and drop designer. So if you ever want, for educational purpose, to play around with qubits and see what your quantum circuit is doing, please visit our homepage. There is a very nice drag and drop design. Thank you for your attention.
Thank you. Questions? I have a question concerning the first part. So what you were showing in terms of the language, that was a classical language, right?
Yes.
I mean, does this also work for kind of quantum languages? So, for instance, if you think about some model where your ground state is not like a stabilizer, but some vibration-free ground state or something like that?
No, because our pre-Hilbert spaces are in that sense characterized by classical states. So if you have an NP-hard problem, the ground state is a classical answer to our solution.
Like this one letter stage theories that we work on. I mean, could you also implement that one?
No, it's because there the gauge symmetry is of different type. So yes, the answer is I can only do it if I can express my local gauge symmetry in terms of a Boolean expression, like for Toricode, for Fibonacci anyons, like for all dimer configurations.
Okay, classical Boolean function. Classical Boolean function.
Classical Boolean function. Yes, a classical Boolean function. It's already interesting enough because these Hilbert spaces are no longer tensor product spaces. It's this gauge symmetry which is then built in. Yes, we didn't try to extend it to. Oh. Okay, I have to think about it. Yeah, we can discuss.
The question for the first one, I'm not sure if I completely understood that. So does this take into account the long-range tail or only the?
So all the rigorous proof is just with the PXP model. If you include the long-range tail, then you will get a slight degeneracy of your system. And you have to check whether you have to start to optimize it. How far can I move everything around that I'm still blockaded, but my long-range tail doesn't matter. So in that sense, you have a proof, do it, then you know in PXP, this is the exact degeneracy state. Then you add the van der Waals interactions and it will start to split. And then it's possible to optimize a little bit the positions, moving them around. Again?
It can be quite tricky to find out the two graphs.
Yes, I mean the goal is then you have this large gap. You have near ground degeneracy due to the van der Waals interactions. And then because you have the large gap, the true ground state, when you have or add a Rabi frequency, should still be larger than the splitting of the van der Waals interaction.
Very nice stuff. So the experiment, what was the largest size that they had?
Oh, so experiment for
the second.
Oh, the second part is pure theory. I apologize.
So,
so there is the proof of principle, which are 3 lattice sites.
just a no, we looked at similar column years ago, and then when you go to the scales of about 50 by 50, is the symmetry with the solar transition, the start having the action, maybe by the slow gets stuff. Then you go there, you don't see. Probably doesn't happen here, but we kind of spent a couple of years seeing that there was type phase popping up only at scales larger than 50 and 50, which is pretty tough to check. And in this case, if you do it with your frustration, because this phases where you cannot check it really by Montagnano. So this is the true ground state. That's right, for large systems beyond. This is very hard to prove. There is not. In our case, there was a very nasty solar transition at 50 by 50 that you don't get if you stay. If you stay anything below 40 by 40, you just don't see. That's kind of one of the weirdness. With this black hat. So otherwise, those states were wonderful and they still exist, but there's many more scarce, but on the cars.
Yes, I mean,
this case is not the case.
With the part experiment on the Boolean is the large table for van der Waals interactions still really remains, or whether it actually disappeared. When we need to find side scaling and look at the influence of the data popping up, we want to screen the box to this analysis. And in infinity on G, yes, it's infinite on a cylinder, there's only 12 around.
So let's see
what let's go. Let's all the experiments to do it and want to see that.
Looking at your low energy state plus can you kind of handle it? Like starting from some and then solving complicated problems, right? And we get state.
Okay, we did. I mean, that's more of German. This question. What we're simply doing next is what happens if you turn on arguments. But the moment the focus is really not reaction, what are the incompatibilities? The next question is what happens if you turn on arguments? Does similar things happen like an experiment that was even trying to like formula on very nice hypothesis case very close to the course. What doesn't it happen to? Naively, I would expect, even just coming on a very weak frequency, I would expect that everything becomes also blind frequency, like we see in the binary universe. If what is very weak frequency, then some state where a, let's say, a kind of solid emergence or a one solid emergence with block-weighting plaquettes, some plaquettes probably have to prefer over can be, but we don't know. That's what it covers. Whether you can use it for annealing, open question.
So can I just can you elaborate what's the difference between what you kind of presented and this harnesses project construction?
I don't think there's so you're very well working with that. I have apologized. We noticed too late. So I think the focus is mainly different that we looked at a local constraint, but for the crossing, and in that sense, I don't know whether your papers really prove that you can do everything, but we made examples of simple expression for the post-Fourier transformation, expressed it in Boolean expressions, how we implement it. And in that sense,
so does your analysis can is this somehow or somehow and just I really at what so is that okay? Is it just short if it's a kind of more general
I think there's different focus for the questions. For you, it's really more frontal computation, more the NP hard problem. For us, it was the local constraint and the Schmuke, whatever we wanted to do. I hope that the indicators from my analysis are so complement to each other.
Okay, can I then ask a question, final question? So you showed this in your first part, this toric code reduction or like pre-Hilbert space, and you said this is the minimal version. In which sense is it minimal? Is it like by sort of brute force search, or is there like a deeper meaning to the word minimal?
No, it's a rigorous proof.
Oh, I see.
So you start with, let's take 3. Can I express the Boolean expression? And the answer is no. Then you add one addition. Do I have enough degree of freedom to satisfy the constraints by the Boolean expression? And then you do each number of atoms rigorously as a proof until you find the proof fails. And then it's search, can I find a configuration with this many amount of atoms? And whenever the proof fails, then we found one configuration. And therefore, in that sense, it's rigorous, mathematically rigorous proven. There is no way to make it with fewer degrees of freedom.
Good. Cool. Then let's thank Hans-Peter and all the speakers.